Have you ever stared at the back of a snack wrapper and just wondered what all those numbers and words really mean? Well, today we're going to peel back that wrapper and get into the hidden chemical story of the energy inside the food you eat. It all starts with one very common word.
Right, that word, calorie. You see it everywhere, but what is it really? It's not an ingredient you can taste or a vitamin you can see. It's a unit of energy. And to figure out where that energy actually comes from, we have to zoom way into the invisible world of chemistry. You see, to get to the bottom of this, we have to start with the absolute basics, the atoms that make up our food, and the chemical bonds that hold them all together. And honestly, the best way to think about these bonds is like they're the universe's tiniest little batteries, each one just packed with potential energy, waiting to be used. And yep, there's an official name for this. It's called bond energy. It's the specific, measurable amount of energy that's locked inside every single one of those connections. Every sugar, every protein, every fat molecule in your food is just this incredible web of these tiny energy-filled bonds.
Now here's where things get a little weird, maybe even a bit counterintuitive. To break a chemical bond, you actually have to put energy in. Think about stretching a rubber band until it snaps. You have to use energy to do that. The real magic, the big energy payoff, comes when new, more stable bonds form. That's the snapback. That's the moment the energy is actually released. It's all about the difference between the energy you put in and the energy you get out. And when a reaction gives off more energy than it took to get it started, scientists have a great word for that: exothermic. Exo means out, and thermic means heat, so heat going out. You know, your own body's metabolism is just one giant constant series of exothermic reactions, breaking down food to release the energy that keeps you warm and lets you move. Okay, so we know the energy's there, locked away in those bonds, but how on earth do you measure something you literally can't see? How do you put a number on the energy from one of those tiny chemical batteries? Well, they use this incredibly clever technique called calorimetry. It's kind of a genius, indirect way of doing it. You basically trigger a reaction, like burning a little bit of food inside a container that's surrounded by water. Then you just measure how much the water's temperature goes up. The hotter the water gets, the more energy was released. It's so simple, but it's brilliant. And it all comes down to this one little formula. Now, I know it might look a little intimidating, but trust me, it's way simpler than it looks. We're solving for Q, which is the heat. To find it, you just multiply M, the mass of the water, by C, which is a special number for water's heat capacity, and then by delta T, which is just the change in the water's temperature. So in our example, we've got 50 grams of water and its temperature went up by exactly 10 degrees. You plug those numbers in, do the math, and bam, 290 joules. Just like that, we've taken a simple temperature change and turned it into a hard, concrete number. We've actually measured the invisible energy. So, we can measure the total energy that gets released. That's great. But different molecules have different amounts of energy packed inside. So, before you can understand the energy of a substance, you first got to figure out, what is the substance? It's time to play chemical detective. And this is basically part of their detective kit. They can use these simple tests to look for clues. For instance, if you add some bicarbonate to an unknown substance and it starts fizzing, bingo, that's a dead giveaway you're dealing with a carboxylic acid. It's this kind of smart detective work that lets you identify the molecule first. Okay, now let's bring all this lab stuff back to your kitchen. We've seen how energy is stored in bonds, how it's released, and how scientists can measure it in a lab. So now it's time to connect all those dots. Let's take all the science and apply it directly to something like a granola bar in your lunchbox. And here is the big reveal. That calorie you see on a food label, the one with a capital C, is actually a kilocalorie. It's 1,000 times bigger than the little c calories scientists use in the lab. It stands for the amount of energy it takes to heat up 1 whole kilogram of water by 1 degree Celsius. So, how does this break down in our actual food? Well, check this out. Proteins and carbohydrates both give you a solid 4 calories for every gram. But then you look at fat, whoa. It's packing a whopping 9 calories per gram, more than double the others. That's because fat molecules are just loaded with these high-energy bonds, making them an incredibly dense fuel source. All right, it's time to put it all together. Let's take the nutrition info from a real granola bar and do the exact same math that food scientists do to figure out that number on the label. It's really just some simple multiplication.
First, we've got 6 grams of protein, so we multiply that by 4, and we get 24 calories. Next, 25 grams of carbs, times 4 again, gives us 100 calories. And finally, the 8 grams of fat, times that bigger number, 9, gets us 72 calories. Now, all we have to do is add those 3 up.
And there it is, 196 calories. See? That number on the wrapper isn't just a guess. It's a direct calculation based on the chemical bond energy packed inside all those ingredients, ready to fuel your day. But what does 196 calories actually mean in the real world? It's kind of mind-blowing when you think about it. It is enough energy to take 2 whole liters of water, like a big soda bottle, from freezing cold all the way up to a rolling boil. All of that power is just sitting there in one single snack bar. So the most important thing to take away from all of this is actually really simple. The next time you eat anything, just remember you're not just eating food. You're unwrapping a delicious, cleverly designed package of chemical bond energy. And that leaves us with one last big question to chew on. We've cracked the code on the energy that's on our plate. But if we can understand and measure chemical energy with this much precision for our food, what does that mean for everything else? What other kinds of amazing energy packages for our cars, for our homes, are we on the verge of creating for the future?